Hello, wonderful people. Welcome to Cosmology Talks. Today we have Abby Lee, who is a PhD student at the University of Chicago. She's joined by Wendy Freedman, who is a professor in Chicago, and Barry Madore, who is a research astronomer at the Carnegie Institute for Science. Abby is talking today about the J-region Asymptotic Giant Branch, or JAGB, which is a very new distance ladder technique to measure the expansion rate of the universe. In fact, the paper Abby is talking about has one of the first high-precision measurements of the Hubble parameter using this technique, and it is the most precise to date. This is really cool, especially considering that this distance ladder technique might be the one with the most promising future, because the stars it uses are numerous and bright, meaning the technique should ultimately be reliably available out to quite large distances. So this is another case where we get to witness the birth of a new cosmological tool that will go on to achieve great things. And in this case, the new tool arrives with a bit of a bang because the distances Abby measures with JAGB and the Hubble parameter it ultimately gives appear to have significant implications for the Hubble tension. So, on that note, welcome Abby, Barry, and Wendy. Do you want to start by telling us briefly about your paper?
Yeah, thanks for inviting me. I'm really excited to be talking about some of our group's recent work on this new standard candle that I've been trying to help develop for the basis of my thesis work. So, I first want to just shout out the other members of the Chicago Carnegie Hubble program. That's the project that I've been working on for the past 5 years to measure the Hubble constant with JWST data.
Cool. So, if people are thinking of this talk or your paper 6 months or a year from now, and there are only two things they're able to remember, what would you like those two things to be?
The JAGB method is a really promising new standard candle that I think, when combined with this decade's next generation near infrared space telescopes, has the potential to measure incredibly far distances. And also, it's demonstrated really excellent accuracy and precision in the past 5 years. And that's really exciting. And then also, as Wendy talked about last week, I think it's a really interesting result that the TRGB and JGB distances we've measured with our group agree really well, but they don't necessarily agree as well with the cepheids. And so I think that's probably the biggest result of our program. And you can watch their video more if you want the details about that.
Yeah, okay, cool. Let's get into the background and the motivation then. I guess the Hubble parameter doesn't need too much motivation is an interesting thing, but the method in particular you'll be talking about, it would be nice to know exactly why it's so promising and why you chose to spend your PhD on this and not some other method.
Yeah, this story I think really starts in 2019 because in 2019, Wendy and the CCHP released this paper that showed that if you measure the Hubble constant with the tip of the red giant branch distance indicator instead of the cepheids, there's not really a significant Hubble tension. It's only 2 sigma. And this was in 2019. And so, to go into a little bit more detail about that, this plot on the right is showing distances measured to the same galaxies using the cepheids on the y-axis and then the TRGB on the x-axis. And they noticed that for farther away galaxies, so at around 10 megaparsecs, the tip of the red giant branch systematically predicts distances farther than the cepheids. And this is basically where all the supernova host galaxies lie, past 10 megaparsecs. And so understanding okay, what is the problem here, and having some sort of third independent distance indicator that could act as a cross check for these distances in particular would be really powerful and illuminating. So that's really why I think we wanted to develop this distance indicator equal in precision and accuracy to the cepheids and TRGB.
This plot on the left, I think, is a absolutely fascinating one because if the cepheids didn't exist, you'd look at that and say, okay, science happening, absolutely normal. There's two data sets that are, the probability distribution overlaps substantially. But if the CMB didn't exist, you'd also have exactly the same story. TRGB and cepheids, totally fine, no controversy. But it's just the fact that the cepheids and the CMB aren't consistent. You want to ask the TRGB to make its mind up and pick one or the other and not sit there in the middle.
That was our hope when we started.
Yeah, and well, your method that we're talking about in this video is the one that kind of makes that decision almost. But we'll get to that.
Yeah, we'll get to that. So the stars I'm going to be talking about today are asymptotic giant branch stars. So if you know the HR diagram or color magnitude diagram, they're basically the coolest or the reddest and brightest stars in the HR diagram. And so they're in this upper right corner. So they're incredibly cold and they're incredibly red and bright. There is a pretty strong theoretical basis for these stars as standard candles. They are asymptotic giant branch stars. So this is kind of the basic structure of an AGB star or asymptotic giant branch star. Basically, these stars undergo these thermal pulsations, and during one of which, called the third dredge-up event, the convective layer of the star will actually dredge up carbon products from the helium-burning shell out onto the surface. And so when there's carbon on the surface of the star, it makes the star appear much redder. So these carbon-enhanced AGB stars are now extremely red because of the carbon on their surface. And this phenomenon, this dredge-up event, is only effective for carbon stars or for AGB stars in a narrow range of masses, so about 1.5 to 4 solar masses. And so I think they talked about last week, if you have more massive stars, what happens is this thing called hot bottom burning, whereas the carbon is being transported out onto the surface. The star is so hot because it's so massive that the carbon is converted into nitrogen. And then for stars less massive than 1.5 solar masses, basically the dredge-up event isn't effective enough to create this carbon star before the star dies. So there's this really narrow range of masses, and now the star is much redder for carbon stars compared to other types of AGB stars. So this theoretical prediction is reflected observationally really well. So this is a color magnitude diagram. So up is brighter and stars on the right side are cooler or redder. And basically this method uses the carbon enhanced AGB stars that I was talking about in the last slide. And we've seen that these carbon stars in color magnitude diagram space, you can photometrically select them just using infrared color. So you don't need any sort of expensive spectroscopy. And it's been shown that once you select these stars, so the carbon-rich AGB stars are in the light blue, basically the mode or the mean of this distribution, so this is the luminosity function for the stars within this light blue. So the mode of this distribution is constant from galaxy to galaxy and therefore an effective standard candle. And this has really been like the basis of my thesis work, as I said before. And it's also been shown that this method has comparable accuracy and precision to the TRGB and cepheids, and I'll talk a little bit more later how we know that.
I guess the second point here is one that if you're not going to go into more detail otherwise, can I ask a question about it? You say that they are photometrically selected. I mean, is it literally just from this diagram that there's like a cut on the x-axis, or?
Yeah, so in practice, it literally just means like the stars are between like 2.3 and 3 in this color magnitude diagram. So it's like super simple.
So point 2 is literally saying you do this blue band and you only include the black dots inside the blue band.
Exactly.
And then you plot up this histogram of stars on their y-axis values, and it's where the peak of that is your distance indicator.
It's definitely the most simple out of the 3 distance indicators, I think. So yeah, now I'll be talking a little bit about where this method came from, because it definitely didn't come from nowhere. Actually, in the 80s, a paper by Harvey Richer actually looked at a carbon star bolometric luminosity function, and so that's this plot. And he just noticed that when you plot like a histogram of carbon stars, the luminosity function's symmetric and it's bright. And then, in the late 80s, a few papers came out, especially this one by Cook, who looked at the carbon star luminosity functions in several different galaxies. And that's when he first noticed that they all looked pretty similar, and he speculated that this luminosity function could maybe be used as a distance indicator. And then in the early 2000s, this seminal paper by Weinberg and Nikolaev, they, for the first time, used carbon stars to measure distances in the near infrared. So this plot, and this is important, when you have a K versus J minus K color magnitude diagram, there's like a color magnitude relation. So the carbon stars, you can fit like a line through their K versus J minus K relation. And that can be used to measure distances. But after this paper came out, no one really used this method, mainly actually because there just wasn't a lot of near-infrared data to test this method out on.
Can I maybe just ask a naive question about the Weinberg and Nikolaev plot? How were those black dots isolated from all of the black dots? So, like, how were those stars isolated?
Yeah, so I think they basically had like a sample of Miras or like long period variable stars, and then that's like all the black dots, and then they just fit a line to the black dots within these two dotted lines.
You might point out too that in the color magnitude diagram they had thousands of stars right across the color magnitude diagram, and they divided the galaxy into different regions, and they noticed that there was this really tight relation over this color range, had a very small dispersion.
You can see it hiding in the background. Those contours are of the larger population of stars in the Large Magellanic Cloud.
Yeah, that's what I was wondering. I think you did just answer me, but I probably didn't understand the answer. How does one pick out these black dots from the thousands that they have?
So I think they use like known Miras to figure out what colors they should be using to select the carbon stars
Okay, so there is a way of isolating the carbon stars.
with colors. Yeah.
So, I haven't looked at this paper in a little while. So the contours there, I'm not sure what the black dots that they plotted are and how they're representing but going back to what you said, John, earlier, you can see it in the color magnitude diagram. When you look at that distribution of stars, it's quite clear that there's a slope and a small dispersion in the K band versus J minus K. And what they're actually representing with those dots on the contours, I'd have to look at the paper again.
The contours are for the total ensemble of data in the Large Magellanic Cloud. And I think that they were trying to make the point that those are carbon stars, which had been found from spectroscopic observations. So that's why the sparsity of objects there, that there are oxygen-rich ones, which form a plume which is basically vertical over to the left, and the carbon stars in the classical sense of spectroscopically confirmed carbon stars come in across that region. Not very well defined, but at least it's telling you that those are carbon stars and you should be wondering about their properties photometrically. So you could call them carbon stars. We didn't originally call them carbon stars, we just called them J branch JAGB stars because they were photometrically selected.
Yeah, they defined that population, very clearly. and the beauty of it, as Abby said, is that you don't need very expensive telescope time follow-up spectroscopic observations. You can identify them purely on the basis of their luminosities and their colors.
The early studies that Richer and others were doing were based on really hard work with spectroscopy, which meant it was never going to go anywhere in an extragalactic sense because you could never follow them up spectroscopically.
And they also developed a medium band photometric system to identify the carbon and titanium bands, so that it was a poor man's way, essentially, of doing spectroscopy and identifying these stars. But they didn't have to worry.
Anything that requires spectroscopy or even narrow band or moderate band photometry rules those things out as being extragalactic distance indicators because you just can't get the filters and the amount of telescope time that you need. Nikolaev and Weinberg were using broadband filters, which was very highly efficient. And so suddenly that opened up the window.
When you say you just can't get the telescope time, is it, however, true that in a perfect world where there were 1,000 JWSTs and 1,000 Hubbles and blah, 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 that this would be like a wonderful distance indicator if you literally could confirm spectroscopically all of these as carbon stars, or is it not actually adding that much?
Not adding anything in terms of measuring the distances. These stars are well defined on the basis of their colors, and you just need to have similar populations in each of the galaxies that you're studying, and then you do a relative comparison, and the spectra in the context of the distance scale really don't add anything.
Okay, I guess I was just naively looking again at the Madore and Freedman plot. That bulge is clearly there, but maybe if you didn't have the carbon J-band stars, there'd still be scatter from the rest of it, so it might have improved the accuracy somehow, but I guess
I would put money down that every one of those stars, if you went and observed it spectroscopically, you would find it is a carbon star.
I want to point out, like Wendy said, this is just a purely like empirical method. So JGB stars doesn't necessarily equate to carbon star, but it's pretty close.
And the other thing to be said, Sean, about the scatter that you're pointing out is that these stars are somewhat variable. So you can decrease the scatter if you can get multiple observations. You don't require it, but you could decrease the scatter with more telescope time.
I see. When you say they're variable, you mean like if you were to plot where it shows up on the J and J minus K, it would be kind of moving around with time. I see. Okay.
Well, I was just going to say, it's rather remarkable. I mean, the dispersion is about 3/10 of a magnitude, which is very small. And considering the numbers of these stars that are located in these galaxies, statistically, you can define the luminosity, the mode of the distribution really well, as I'm sure Abby will explain.
And there is no theory that predicts a star could be at those colors and luminosities if it's not a carbon star. They just couldn't get that red without having that influence of the carbon on their atmospheres. So it's all self-consistent with calling them carbon stars. But you have to be careful because there are these extreme carbon stars slanting down to the right. You don't want them because they're at a different stage in their evolution.
In 2020, Wendy and Barry, and actually another group simultaneously, showed that in the J band, so this is important, the carbon stars don't have color dependence in their magnitude. So like in the K band, they do, and you have to calibrate that slope. But in the J band, you can just use the mode of their magnitudes. And so that was really powerful. And the same year I started grad school, and that's what I've been working on for the past 5 years, is trying to develop this method from its infancy and prepare it for a Hubble constant measurement with JWST. This is a plot just comparing the brightness of these carbon/JGB stars to the cepheids and TRGB, which are more conventional distance indicators. So they're about a magnitude brighter than the tip of the red giant branch in the near infrared, and about the same brightness as like a 20-day cepheid in the J band. But it is important to point out that when you do cepheid measurements, you need at least 12 epochs of data to measure their amplitudes and periods and phases. And so overall, carbon stars actually require a lot less observing time than cepheids to measure the same distance. And then obviously they can measure much farther distances than the tip of the red giant branch. So I think observationally, they're the cheapest distance indicator.
When you say obviously they can measure to larger distances, is that just because they're brighter?
Yeah.
A naive question then. When you say, okay, to do the cepheid, you have to look at the cepheid at least 12 times to get its time dependence. You also need many, many more carbon stars, though. But does it work with just the way a telescope works, that you look at a region of the sky and you kind of get all of the stars for free? You don't have to look at each one individually.
Well, it's more like with JWST, so you point at the galaxy once, and then you have everything you need for the carbon stars, or one epoch. But for the cepheids, you need to re-observe that field like at least 12 times. Or a lot of the spiral galaxies we've been looking at have at least like 5,000 carbon stars in a single JWST point.
And how many cepheids?
Like at the most like a few hundred, but on average it's more like 50 to 100, I think. Yeah, so that's what the biggest advantage, I think. But some of the other advantages are that they're distinctive and they're easily identifiable on the basis of their color. So like we were saying, you don't need any sort of expensive spectroscopy. And, for cepheids, finding them and measuring their periods is actually not trivial at all. Like it's extremely complicated and there's a lot of choices that you need to make. But for JGB stars, you just select them using their colors. They're ubiquitous and you can find them in all galaxies with significant intermediate age populations. And that's unlike cepheids, which you can only find in face-on star-forming galaxies. Because you're doing these measurements in the near infrared, that's really going to decrease effects of extinction and dust And then, like we were saying before, you only need one epoch of observations for this measurement. And finally, you do this measurement in the outer disks of galaxies, and I'll talk more about this later, but that's really going to decrease effects of crowding compared to the cepheids again, which you can only really find them in the crowded areas of galaxies.
Okay, just as a complete naive outsider, the third point wouldn't have been something I'd have known in advance, but is it just true that dust is less visible in infrared?
Yeah, or the effect is smaller. I think the power of this program, though, is that these three methods are completely independent. And so you can use them as cross checks for each other. So, for example, the place where you do the measurement, the tip of the red giant branch, you're ideally doing that in the outer halo, cepheids, in the inner parts of the galaxies, and then the JGB in the outer disks of galaxies. So the location is completely different. The stellar population is completely different. So for the red giant branch stars, that's an older metal poor stellar population. The cepheids are a younger metal rich population, and then the carbon stars are an intermediate aged stellar population. And finally, the astrophysical mechanism by which these are standard candles are completely independent. So the TRGB is the helium flash in the core of low mass stars. Cepheids are distance indicators because of these mechanical pulsation cycles in their atmospheres, and the JAGB method is based on this third dredge-up event in AGB stars, like we were talking about earlier. So if there's any systematic related to any of these things, like crowding or metallicity, when you compare all their distances, you would be able to see an effect. Like if the cepheids were being affected by metallicity, for example, and their distances in metal-rich galaxies were like systematically different than the TRGB and JGB distances, you could start to suss out, oh, maybe that's a metallicity effect going on.
Just another naive question about the JAGB being measured in the outer disk. Is that literally just because of crowding? Like, it's not that you expect there to be more in the outer disk rather than inner disk from some stellar formation first principles, or?
So yeah, AGB stars can be found throughout the entire disk, but we actually exclude the inner disk when we do our measurements to avoid the crowding. And I'll show what I mean by that later. Yeah.
And sorry, another naive question. The reason you can't do that also for cepheids is just there aren't enough cepheids that you can find them in the less dense areas where there are fewer stars.
Yeah, they're really young, so you can only find them in active star forming regions. Yeah, which are going to be the areas with the most dust and the most stars. So, they're going to be the most crowded because of that. Yeah, like I said, the bulk of my thesis work has been trying to figure out if the JG method is as accurate as the TRGB and cepheids. And one way that I did this was by measuring distances with the JG method to nearby galaxies that have pretty well-known distances, and comparing them to TRGB and cepheid distances. And so one of the major results was I found that in nearby galaxies, so closer than about 4 megaparsecs, the JWST method agrees really well with the tip of the red giant branch at better than like a 3% level. And so any systematics like, maybe a metallicity effect, for example, would have shown up in a plot like this in a comparison with the tip of the red giant branch, but we're not seeing any systematic effects. Also, the scatter is really small in this comparison. And so this showed us that the JGB method is comparable in accuracy compared with the tip of the red giant branch in this sample of galaxies.
Another naive question. When you say 3% level, are you meaning like in the trend or even in the scatter that there's never more than a 3%?
This bottom panel is showing like the difference between the JGB and TRGB distance moduli. And so the residuals about this relationship.
Because it doesn't look like 3%, right? Like it looks like 10%.
3% in distance.
Yeah. Okay. Right. So 10% in distance modulus would equate to about 3% in distance. Do you mean?
The sigma of 0.07 in the left-hand panel equates to a 3.5% sigma in distance.
And sigma is the standard deviation of
the scatter in those data points around the line.
And just to add, so what Barry and I did early on was to use data in the literature that people had published primarily for other reasons, studying stellar populations. And what Abby has done in her thesis is to use a consistent set of data from a telescope at Las Campanas and to measure them all in the same way. So it's a self-consistent study, and further showed how well the method works.
So I was just going to say, if there are other factors entering into one or the other of the distance indicators that had any major impact, they would increase the scatter in that relationship. And so everything, whether we've thought of it or not, is contained in that 0.07 magnitude scatter, including the photometric errors.
And then this group did a similar study with cepheids versus JGB. And they found a similar scatter. Yeah. So now I'll be talking about the actual paper because I just wanted to give an introduction to the method. But I think the major result from my paper was really emphasizing that, like I was saying before, you want to be doing these measurements in the outer disks of galaxies. So this was one of our galaxies that we studied, and this was our JWST near camp pointing, so this rectangle. And we only use data outside this circle. So, and you can see why. So this is a color magnitude diagram of all the data inside the circle, and this is the data outside the circle. And what we were seeing is that the mode of this distribution for the inner disk was much brighter. So in this galaxy, it was, like 0.15 mag, which is like 7% difference in distance. And this, like, the dispersion of this luminosity function was also much larger. And so this is showing you that, like, measurements with the JAGB method in the inner disks of galaxies will be really biased. And so you have to be really careful with that.
What you're saying looks correct by eye. Just trying to pass the numbers.
This is showing the mode of the distribution, which is the actual distance indicator. So the mode in the inner disk was 25.27, which is about 0.15 mag brighter than the mode in the outer disk.
And that equates to the 7% difference in distance. I see.
And also the dispersion of the luminosity function. So basically the precision of the measurement is going to be worse in the inner disk too. And we have been doing outer disk measurements, but previously we would kind of do it by eye. And I think it's close. Like, you can see in this image, like, where the disk of the galaxy is, but we wanted to standardize it. So we wanted to create a methodology that, like, was repeatable or reproducible.
But a hint of what's going on is, if you take a look at the left color magnitude diagram, at around 27th magnitude, the counts are falling off precipitously, right? And at 27.5, they're gone. In the outer disk, you're getting much deeper. And that tells me that something's going on in the photometry due to the surface brightness making it harder and harder to measure stars in the inner disk. And the potential for crowding is going up because the surface brightness is rising. And if you crowd something and make it brighter, the stars get brighter. And if you crowd them randomly, then it will have the potential of making that distribution wider. And those are the two measured properties of the new AGB histogram in the inner disk: wider, brighter, distinctive signature of crowding.
Yeah, and also, I didn't say this before, but the way we measure the statistical error on the measurement is basically like the error on the mode. So it's basically like how wide the JGB luminosity function is and how many divided by the square root of how many stars go into that. So a wider luminosity function will mean a larger statistical error. So that's why this is less precise than that.
And maybe also just to add, sorry, Abby, a lot of times in the inner disk, there are asymmetries that you see in the luminosity function, and you don't tend to get those in the outer regions. It becomes much more symmetric, as well as having a smaller dispersion.
Yes, that's very true. So, like, there were, there's like structure, like there's this little bump that in the inner disk, that's not, all the luminosity functions in the outer disks we were seeing were super self-similar and like symmetric looking. So what could this be due to? Probably crowding. And this is another supernova host galaxy we were looking at, and you can just see, like in this zoomed in panel, there's just way more stars, and you can just tell like it's going to be a lot harder to measure the luminosities of these stars in the inner parts of a galaxy than the outer parts. So this was the actual cut we used, so we're only using stars below that cut. And all the cepheids in this galaxy are found in the disk, and so you can start to see, like, of course the cepheids are going to be more affected by a crowding systematic than the JGB stars. How do you know where the outer disk is? Basically, we measure the JGB magnitude in spatial bins. So imagine like this first data point corresponds to the 500 innermost JGB stars. And then the second data point is the next 500 innermost JGB stars. And so we're basically doing like JGB measurements in overlapping ellipses in every galaxy. So this last data point is going to be the outermost 500 JGB stars. And we saw that in all the galaxies, or in most of the galaxies, there's this convergence pattern where the JGB magnitude would eventually stabilize to the same magnitude. And we can actually quantify when it stabilizes by taking the derivative of this relationship. So this is the JGB magnitude with respect to radial distance, so how far away you are from the center of the galaxy. And when this bottom panel is showing the derivative of that. And so the first zero crossing of the derivative is when the JGB magnitude really converges to the same value. And in galaxies where we weren't observing this convergence pattern, we discarded. And there were 3 out of 10 of the galaxies. That's what happened to them.
And it's important to add that that decision was made before any application to determining the Hubble constant. So it was, doing these convergence plots, you decide which is the good sample, and then thereafter that was the only sample that went into the determination of H0.
Just playing the game of like trying to think of things that might have gone wrong. Is there any reason why that might have introduced a bias, that the sort of galaxies that haven't converged by the statistic might be expected to be the galaxies that would give you, smaller distances and therefore larger H0s? Or is this?
Yeah, so we did an H0 measurement with including them and with excluding them. I do want to point out, like, those 3 galaxies actually had astrophysical explanations for why they should have been thrown out. So like one of them was in a merger with another galaxy, and so like there was no clear outer disk because the 2 galaxies were merging with each other. Another galaxy had been basically, there was no like JGB there was no intermediate age population because its star formation had been quenched like 500 mega years ago or something. And so there were like very clear astrophysical reasons. So that was reassuring. But also when we did an H0 measurement, including those galaxies, I think it was like 68 versus 68.8 in Hubble constant or something. So including them did raise it, but not significantly. Okay, so yeah, this is the final result from this project. The paper was measuring the distances, and then in Freedman 2024, which was the CCHP results paper, where we actually used these distances to calibrate the supernova absolute magnitudes, we measured a Hubble constant of 68. And you can also find in this paper the comparisons with our JGB or Cepheid and TRGB distances. And like I was saying before, it's really interesting that the JGB and TRGB distances agree super well, whereas the JGB and Cepheid distances disagree a little bit more. And I think, we're chipping a little bit more away at like what is happening here, because we know, it's interesting that the JGB and TRGB agree. And these are the 2 distance indicators that are looking at the least crowded stars. So yeah, I think we have some clues to what is the cause of this Hubble tension, but we don't know for sure yet.
Sorry, first of all, someone has left a YouTube comment on Wendy and Barry's talk last week saying that you would be deducted marks if you were undergraduates doing your error analysis for having too many significant figures. So I just thought that would be amusing to point out. But I can imagine how the statistical number here is arrived at. That you've got a distribution; it's the width of the distribution. What is the physics or the thinking or the calculation, whatever, that's going into this 1.9 value for systematics? Where does that come from? How do you estimate it to be that magnitude?
So the systematic error is coming from the 0 point calibration of the JG method. So I didn't talk about this in this talk, but basically you have to calibrate the absolute luminosity of the JGB stars in a galaxy where we know its distance. It's through a geometric distance indicator, like a water megamaser, for example. So that distance to the geometric calibrating galaxy NGC 4258, that is a systematic error, because if that distance is wrong, then that throws our whole Hubble constant off. And then if there are any errors in that, like when we actually do the JHB measurement in that galaxy, if anything's wrong with that, that's also a systematic error. So all the systematic errors are coming from our JHB measurement in that one calibrating galaxy.
That accounts for all 1.9.
Well, and there's also the smoothing. You allow for that. The fact that you have different smoothing that you can apply when you're determining the mode, and there's some uncertainty in that, and that ultimately goes into the overall uncertainty.
The smoothing affects like those kinds of things in just the NGC 4258 galaxy,
which sets the calibration for everything that follows.
If you were to measure the tip of the red giant branch in the disk, where there's reddening and other effects, and you didn't take it into account, then yes, that would be a systematic error. And our advice is don't measure in the disk if you're doing the tip of the red giant branch. And many groups have decided that, oh no, we're going to measure in the disk, and we're then going to try to fix it. Our fix is don't go there. But what is frightening is how small the scatter is. For the bottom panel, that's an inter-method scatter of 0.03 magnitudes. 300ths of a magnitude is unheard of in the distance scale. And, well, either that's signaling something wonderful about those two distance indicators, or we got damn lucky, or damn unlucky.
If you're only going to take away a couple of things from this talk, I think it's that this new method is really promising, and with JWST, it's going to be incredibly powerful. In the next few years, I think the most important thing to focus on for the JJ method is just getting more data. Because if we want to measure Hubble constant at the 1% level, then we're going to need a lot more galaxies to do this measurement in. So
I don't know whether I've just giving into recency bias because I've just spoken to all of you, but is this like the method of the future? Like it seems like it's the one that has the fewest downsides, and that maybe 10 years from now, JAGB is the one that will be the kind of gold standard. Will it be the gold standard because it is the one that won't have crowding and can go to larger distances? And
yeah, I mean it is the newest, so it's only been being tested for like 5 years. So I think that's its main disadvantage. But like, and the cepheids have been being tested for 100 years. But yeah, I think with the Roman Space Telescope and Euclid and James Webb Space Telescope, yeah, I think the JG method is the most exciting one to me.
Right, because everything will get better, but it looks like the like upper limit for how good this will get is much higher than the others, just because they're the brighter ones, they're more common than cepheids.
Yeah, that's my opinion. I don't know.
So I guess I would chime in and say that I think all of these methods are going to have their own systematics, and I think it's the combination and the fact that you can measure them in the same galaxies. And this is really the first time we've been able to do this. Many methods can be applied at different distances to different galaxies, but when you have the opportunity to measure the distances in single galaxies, you really have the opportunity then to constrain the systematics, and that's what gives you, or at least gives me, the confidence that you will have constrained them. And as Abby said, I think the future is increasing the sample size. This is the first step, and we will continue.
And part of the future, I hope, is that it will spawn interest in the theoretical community to better understand the carbon stars. I wouldn't want to do it because the atmospheres of carbon stars are probably the most complex in the entire color magnitude diagram. And they are pulsating at the same time. And as they develop winds and they produce dust. So they are very complicated, but they seem to be universally complicated in a way that preserves an element of simplicity.
Okay, and Abby did give in her introduction what seemed to someone who has never worked in stellar modeling a compelling theoretical justification for why you do expect this kind of bulge in the diagram. So I guess theorists aren't completely baffled by this, but you're just meaning like understanding it even better would be even better.
Well, the history has always been a back and forth with the theorists. You get better observations, and then they get better theories to approximate the observations, and they learn something and we learn something. And so I hope that continues, and it would be nice to have a theory behind it. But in the end, some things just are matters of fact, and whether you understand them completely or not becomes irrelevant. Nobody understands the cepheids that well, and yet they are and have been the gold standard for a very, very long time. We don't even know what the masses of cepheids are.
If I remember correctly from the video from last week, the reason why you're only using the one calibrator galaxy,
there's usually like 4 galaxies where people, or there are 4 galaxies where people do the geometric calibration. But JWST stars are so bright that 3 of the galaxies, one them being like the Milky Way, so our own galaxy, the Large Magellanic Cloud, and the Small Magellanic Cloud, they're so bright that they would saturate if we observe them with JWST. And you would also, like, it's such a close galaxy, you can't get the whole galaxy with one JWST pointing. You would need like many pointing. So that those 3 galaxies are going to be a little bit more complicated. We're going to have to like derive, JWST to ground-based photometric transformations, because we're probably going to have to observe them with ground-based telescopes instead of JWST. So it's just a little more complicated, and we're going to have to account for more systematics in that. But I think that's definitely like also a big next step for all 3 methods.
So is this something, I mean, that seems like equally important because the 1.85 and 1.9 are roughly the same number. So it seems like you want to drive both of them down, not one at the expense of the other. So is that something that's coming in the future?
Yeah, I would say they're definitely equally important.
Yeah, and the other thing to be said is that there may even be systematics in the sample of galaxies that have the type 1As, for which we can also measure the JAGB and TRGB and cepheid distances. And there's some indication now that the nearer ones in that sample have brighter supernovae. And whether that's a statistical effect or whether that will end up being a systematic, that somehow perhaps if the distances are less certain or the supernova measurements, that you could have a systematic that would show up when you have better observations. And so that will become clearer in the next few years as more JWST data are obtained for those galaxies.
Awesome. So let's wrap things up. What work being done in cosmology at the moment do you find particularly interesting but underappreciated by the rest of the community?
I don't know if it's underappreciated, but I think the work being done to measure the Hubble constant with lenses, like gravitational lenses, is so cool. And I looked at one of my friends who's analyzing some of those lensing systems, and it like takes so much manual labor to model one of them, and they have to do like hundreds to get as precise of a Hubble constant, or like a 1% Hubble constant. So again, I don't think it's underappreciated. I think everyone thinks it's really cool, but I think that's going to be really exciting in like the next.
So to clarify, I to make sure I know what you're talking about, you mean where there's like a time delay of strong lensing objects where you see multiple objects?
Yeah.
The length of time it takes the image that traveled the furthest compared to the image that traveled the shortest is telling you something about expansion rate. I see. Yeah, that is very cool. There was a brief period where it looked like they were coming out to get the mid to high 70s with low measurement uncertainty as well a few years ago, and then I guess they had to recorrect certain lens models and it dropped again. But that was very exciting because it looked like the first independent high H0 value, but I guess it went away.
Measuring the Hubble constant is hard. It's really hard.
Thanks everyone for watching. If you like this, please do subscribe and click the bell if you want to be notified of new videos. Click like to help with YouTube algorithms, both for you and the channel, because YouTube will know to recommend more stuff like this. If you have any questions or suggestions, leave a comment. Otherwise, yeah, check out the talk from last week where Wendy and Barry talked about the other two methods, the TRGB and cepheid, as well as this method, and how it all comes together into a kind of combined H0 measurement. Thanks, Abby, Barry, and Wendy for the great talk.
Bye.
Thank you.
Thank you.